Thank you. I'd like to thank organizers for inviting me to talk. So, we'll switch gears quite a bit because this is more of the mathematical talk. Okay, so what I will do is discuss a very simple problem that occurs when you try to do imaging. And that is the following, that if you solve the forward problem and you watch a movie of how waves propagate, it's kind of natural to think, well, why cannot I reverse that movie? And this reversal, of course, will reveal the structure for which scattering occurs. The problem is that mathematically what you need to do is ill-posed, and that has been an obstacle in all imaging methods, and that gives me a chance to go over these methods rather briefly, and then I'll turn to a new approach which allows you to do this reversal effectively. So the seismic inverse problem has two parts. One is linear but ill-posed, and therefore direct numerical implementation of it cannot be done. You have to modify the problem. And then there is a nonlinear part where you try to estimate the parameters of the background, which in seismics is called velocity estimation. The velocity estimation currently is done more or less manually. That is, people have to participate in this process. It's not like you push a button and this velocity will come out. Of course, there are tools for that, but nevertheless, it's manual. And the problem, the linear part, is migration, or what's called migration. So I will talk a little bit about how different methods of imaging overcome this ill-posedness, and then I turn roughly one half of the talk will be a description of the new method and the consequences as far as what algorithms you need, and I'll show some pictures. So, well, when we record the seismic ground, this always happens on some surface or line. That's generally the case. So the data is a function of time, we collect a spatial surface. So natural question is to ask, well, we're going a little below how the field will look like, so-called surface thinking. And the answer to this problem, to this question, leads to an ill-posed problem. It's in mathematics, it's known as a example, and we'll go over it in minutes. So let's take this equation as the equation governing the wave propagation. So it's a system equation with just one parameter, which is velocity or index of diffraction. The forward problem to consider is a half space. The forward problem is formulated with the half space on the surface of it will have zero pressure, and it's a well-posed problem. We can always solve that. The measurement has to be done a little bit below the surface, because on the surface the function is zero. And there are alternative formulations, but that's what we'll work with. Okay, so we'll apply Fourier transform in time. The equation is modified, you see it on the top. And now we have the equation in depth. And if we want to solve it, it's a second order equation, so we need two initial conditions. This problem is ill-posed. So how is it ill-posed? Well, let's see. So let's take the simple case. Constant velocity, periodic in x variable, so for simplicity, so that we can compute the solution explicitly. We set initial conditions as a Fourier series, and we have explicit solution. So if we look at it, we see that this number kz can be either real or imaginary, depending on the underneath the square root. And if it's imaginary, because there are two modes there with a plus and minus, one of them will decay and another will grow. And so that's the ill conditioning. Now, so if kz becomes imaginary, we have a blow up. And these are associated physically with so-called evanescent waves. So in the forward problem, evanescent waves are exponentially decaying modes. They don't cause much trouble. But if you look at this problem in the inverse problem, one of the modes blows up, and therefore you have to deal with it. Now, if the background is constant, it's very easy to address it. Essentially, you just restrict the computation to the case when k is less than that critical number, and algorithmically it's very easy. All you need to do is to, at each depth step, apply Fourier transform and apply ideal filter, killing all the modes that don't propagate, and that's it. So this was suggested in geophysical literature by Kozlov and Beysal in 1983, and later Natter, who didn't know of this work, rediscovered it and used it in ultrasonic imaging, where the background, constant background, actually is quite reasonable if you do soft tissue inversions. Now, however, in geophysics, some background is not an option. Even using the only depth-dependent velocity is not really an option. So we need to deal with this problem in the more general situation when the background velocity is a function of both depth and lateral direction. So now let's take a look at how different methods deal with this, because there are several methods, and what do we do? So let's start with one of the oldest ways of imaging seismic data, the so-called Kirchhoff migration, or in a more modern interpretation, it's a generalized Radon transform. The differences between the two is in selection of weights, essentially. And what I wrote here is an ansatz for the generalized Radon transform. The reason, I mean, I could have written it without these denominators and without this function h. It will also produce an image, but then there would be variations in intensity within the image. So to compensate, those factors are introduced. H is certain Jacobian, but if you want to analyze this integral, the way you do it, you assume single scattering, and you write in approximation, geometric optics approximation for the Green's function. You substitute it in, then I will have to describe what h is, do some manipulation, and you will find out that you roughly get a delta function inside this integral, and you recover the perturbation. So such schemes have certain advantages. For example, they are not very sensitive to how you select the receivers. They can be on more or less arbitrary surfaces if you do things right. Now, this is for fixed source. You can write it for multitude of sources, multitude of receivers. There is a paper by Bob Burridge and myself around 1990 where we try to push it to significant generality for both acoustic, elastic case. However, there is a limit what you can do with it. And the reason is that you cannot control errors in asymptotic expansions. And while it will produce correct locations for places where there is a rapid change, that is interfaces, and if you choose the parameters, this normalization factors correctly, it will also produce right jumps at those locations, which is much harder given real data because calibration sometimes is not available. There is not much else you can do. I mean, one can improve things a bit, but there is sort of an absolute limit to what is achievable by this type of techniques. Now, why this solves the ill-posedness problem? Well, because we select specific Green's function. This bar flips the phase, and that's what does it. So you select the Green's function which propagates in a particular direction. And that's what, so the problem of ill-posedness doesn't even show itself, although it's there. And it's resolved by simply our selecting particular Green's functions. Then there is another class of methods which are basically splitting methods. You replace wave propagation in two directions by propagation only in one direction. So I chose a very, very simplistic example. If the background is constant, it's fairly easy to do such splittings. And if you look at 1D case, you see that if you then solve first order equation, the wave will go only in one direction. So early work of Claerbout used that. That's more or less how the seismic became computerized. People started to use this one-way propagators. Well, there are several problems with that. So one is that if you have a preferred direction of propagation, waves which don't go in that direction may be attenuated or killed entirely. The problem with that is that if you have really complicated background, waves may go down and then turn. And so those waves will be attenuated, and therefore you will not image corresponding events. Second thing is that if you have variable background, this factorization is actually very difficult. So at some point I was trying very hard to do it. I never managed, and I don't know of any consistent way. I mean, I know how to write it on paper, but I don't know how to do it in the computer in a consistent way. So the results that you get using the splitting methods are quite similar to those obtained by asymptotic methods, provided both are implemented correctly. So, and again, there is a limit of what you can achieve with it. Okay. Now, reverse time migration. So the reverse time migration uses two-way propagation. I mean, a modern version of it doesn't use any square roots of operators. It's really two-way propagation. But it's done by a clever trick where the initial problem on space-like surface is replaced by initial value problem in time. Basically, what you record, you treat as initial condition in time, in reverse order. So you feed it in, propagate the same thing from the source in the forward way, and then at each time you correlate the results. That's basically the intuition. The intuition is correct. It works. The problem is that, and it was introduced by practically the same people who, whom I mentioned before, Baysal, Kozlov, and Sherwood, in about the same time. And basically, it shifts the problem. So you replace the problem that you want to solve by another problem, which is producing something useful. But the so-called law of conservation of difficulty moves the difficulty now in this imaging condition. That is, when you construct the image, you have very little control over these factors that I intentionally showed in the asymptotic methods. You get what you get, essentially. And you can change this imaging condition somewhat, but there is, again, an obstacle. Although, from physics point of view, this is a better choice in some sense, because your propagation actually is achieved in a correct way, except that your amplitudes will be somewhat different from what you would like them to be. Now, localization in this case is achieved by imaging condition in time. What does it mean? It means that if your background is variable, it's very hard to use this to try to estimate the velocity. There are also problems that you have to have huge memory in order to accommodate this type of algorithm, although there are some clever ideas how to reduce the requirement. So this is the sort of, very briefly, the picture of methods that are being used in seismics. So all three methodologies are still being used. It depends what you want to do, what kind of measurements you have. And, well, basically when Christian was my student, we started this, it was 6 or 7 years before, but finally we did it in around 2008. So we constructed a method that actually resolved this ill-conditioning problem. So it's actually quite simple. So in fact, it's very simple. It's again a shift of problem into some other place. So this equation I already wrote, and notice that this operator acting on p hat is a self-adjoint operator. And let's consider the case when it has discrete spectrum. It depends on boundary conditions, how you set up, but in practice it's always discrete. So we have real eigenvalues, and let's assume we have, well, we do have in that case the complete set of eigenfunctions. And we notice, if you go back to that example, I'm not going to go there, that the evanescent, the bad ones, were corresponding to positive eigenvalues. So we introduce so-called spectral projectors. So if you have eigenfunctions, then the operator can be written as a decomposition into these projectors. That's so-called spectral theorem. And the spectral projector is simply combination of all projection on the space of eigenfunction corresponding to some criteria, which in this case negative eigenvalues. So if we surround our operator L by these projectors, all it does, it simply removes all the positive eigenvalues in corresponding modes. So it's very, very simple in that regard. I'm simply suppressing all evanescent waves. Everything that I don't like, I kill. That's it. And then this problem, reformulated problem, is no longer ill-posed. It's fine. So what I did, I shifted the difficulty now in computing this projectors. Okay. Well, it turns out that there are many ways of computing these projectors. A good review of this can be found in Kinney and Lab 1995 they come from control theory, where such things are done. In fact, the way people, there are several areas where people use spectral projectors. One is control theory, another is quantum chemistry. Chemists, well, call it purifying transform. So that's what chemistry entices you to use as far as words. But these are spectral projectors or sign function of an operator. Okay. The projector is related to sign function in a very simple way. Okay. So you don't have necessarily to compute the eigenfunctions in order to compute spectral projectors. That's one of the sort of important observations. For example, this iteration that is written above will converge to a sign function of an operator. So let me give you a proof. Proof is very simple. First, you have to observe that if you have a matrix that diagonalizes, if you diagonalize S0, the same matrices will diagonalize all consecutive iterates. Therefore, the problem reduces to a scalar problem, to the diagonal matrix. Now, as a scalar problem, if you look at it, there are 3 fixed points. It will be 1, minus 1, and 0. 1, minus 1 are stable, and 0 is not. And if you basically launch this iteration, what happens, these eigenvalues of the consecutive iterates walk towards plus minus 1. And that's the sign function of the operator. So it's very, very simple. The price to pay for such things is that you have to multiply matrices. Now, matrix multiplication is order n cube, and therefore unpleasant. However, you can try to deal with that by sparsifying these matrices. And there are several ways of doing it. So, in 1999 we did it in academic type of quantum chemistry, showing that these purifying transforms can be done in wavelet system of coordinates, can be done fast. Now, in wave propagation paper with Sandberg, we used a so-called partition low rank representation of a matrix. That is the following. You split the matrix, say, by half like this, and the corners have low rank, and then you split the rest again. So along diagonal you keep the blocks, but off diagonal things are low rank, and such things can be multiplied. You can have the whole calculus. Now we are currently looking at an approximation that one problem with this iteration is not self-correcting. That is, if I have to maintain accuracy from the beginning. Self-correcting iteration is something that if you know approximate answer, you can plug it in, and then a couple of iterations it improves, and that's it. Newton's iteration is an example of self-correcting. So we're currently looking at approximations that replacing this by self-correcting approximations. Basically, this is the problem that needs to be solved. It needs to be done fast because you need to do it for all frequencies and for all depths. Now, as you go from frequency to frequency, of course, changes are not very significant, and so that's why the self-correcting stuff is useful. So, there is still things to be done. We need to do it in 3D, but in 2D it works. Now, the imaging condition, well, there are many possible ones, and in fact, later on we're planning to try to do velocity analysis with it. But just to illustrate things, this is the imaging condition. Essentially, we kind of compute the gather that would come from coincidence source and receiver. So there is various interpretation of it. I'll just leave it at what this is. Now, couple of details which are very important. Since I'm using second order equation, I need two initial conditions. One is available, that's what you measure, and the second one is not. Typically, you don't measure the normal derivatives. So it is a problem because in order to compute normal derivatives, you need to compute the Dirichlet-Neumann map. Fortunately, for half space, in the constant background, it's easy. This formula gives you the normal derivative. So we deal so far with it by assumption that the measurement is done in a constant background. Now, it's not a bad assumption because if you do marine seismics, water is as constant as it gets. So it's an issue if you do land seismics or something like that, but for the doing it, at least for now, for theoretical purposes, it's fine. So but this needs to be computed. It needs to be computed only once, because once you start marching, you always have that through your numerical scheme. Now, the setup, we cast it as a first-order system, plus the initial condition. Now, how do you solve? Well, we use actually very accurate approach based on parallel spheroidal wave functions. I can tell you that I think in seismic industry there are no accurate codes as far as large models are concerned. And the reason I'm making such statement is a couple of years ago, SAG distributed some models for different groups, like 20 groups, to do some computations. So Christian was doing that. And then he discovered, and it was a very similar situation when the recording or simulated recording was done just below the surface, like it's done in marine seismic. You do it near the surface, maybe 7-10 meters below the surface. Now, because on the surface the value of the field is 0, just the wavelength in water, so if you go half wavelength in water, it's still the value is small. So basically, he discovered that the source was improperly produced for that model that SAG distributed. So he contacted the people who produced it. They first didn't understand what he was talking about. Then finally they understood, they modified the source, but no other company contacted them. So they didn't even notice. So the accuracy of the code currently is about 3 digits, and there is a 3D version of it. The reason for using band-limited function is that you can significantly reduce oversampling. So with oversampling like factor of 3 to 4, you can, well, in the background without singularities, you can propagate, well, with oversampling by a factor of 2 to 3, you can propagate across the ocean, for example. I mean, the numerical dispersion is cut down very, very significantly if you do that. There are simple reasons for that, but I don't have time to go into that. So what I'm saying is that once you start trying to do things carefully, it's very important to maintain accuracy. And maintaining accuracy is hard in areas like seismics because measurements are not very accurate, and so people can be quite loose. And watching presentations at a conference, I can tell you that I'm observing the same phenomena in the areas that were described for the same reasons, because measurements are low accuracy, and so people tend to do a quick job on numerics, which is dangerous. So, and I'll show you some examples of it. So, so this is the algorithm. Basically, if you have sources and receivers, you do source gathers and receivers gathers using these initial conditions and keep marching. So this is the computation, probably looking at it. Notice that you do it for all frequencies and for all depths, so it's a quite significantly large loop. But for 2D problems, it's quite reasonable and you can compute it just fine. For 3D, there are some, well, you need a bigger computer, basically. Okay, so some details. Sometimes this projectors can be reused if sources and receivers are in the same locations. Basically, if the velocity depends on depth, then Kozlov and Beysel solved it a long time ago, and we can use FFT. We also use absorbing boundary conditions on the sides using the variant of approach which has damping layer that preserves the fact that the operator in question is self-adjoint, because we want that. So there are some technical details. Okay, here is an example. So this is the original SAG EAG velocity model, and we chose the slice. It's a two-dimensional slice of a 3D model. We chose the same slice as somebody else. I'll show you some results from somebody else's paper. Now, typically in seismics, when people demonstrate the imaging method, they would use the exact velocity model for the reconstruction. We didn't do that. We blurred it by simply running a blurring filter on it, no sophistication here. And we have two models, these sort of moderately blurred and significantly blurred. High velocity, it's a sol dome. So it's a model of a sol dome. So, so this is the original, and then we blurred it, and you see what happens, the weak interfaces which you see on the side, they simply disappear after such blurring. So this is what you get. Okay, and now you see the reconstruction from the moderately blurred model. On the top, I forgot to say that if you do this Fourier transform type thing for constant background, you can of course try to do it for variable background by using the worst horizontal, lateral velocity, the fastest velocity that you have there, and set cutoff for that. You can do that. It will produce stability, but you will be killing some of the propagating modes by doing so. So on the top is what happens if you do that. And at the bottom is using spectral projectors. Now, when we saw this picture, my first reaction was that probably somehow we use multiple reflections, because there is absolutely no oscillation within the dome. You will see, I will talk a little bit later about this. And this is what happens if we use the strongly blurred model. Now, let's see, if I do it quickly, you can see that, the positions shift. Sort of it kind of sank a little bit. That's because, of course, velocities are not quite right. Okay, so now this is the result. On the top is the result I picked. I chose it from a paper of somebody who was using the same slice. I don't want to go into it's not a true comparison because I don't know details of their numerical scheme. There are many things, but I want to show it for you to see the qualitative difference. You can see that within the sol dome, in our case, there is practically no oscillation. It's clean. And because of that, when I looked at it, I thought we must have been using multiple reflections somehow, because, well, it's too good to be true in some sense. Well, I don't know. Well, it turns out we didn't use multiple reflections, and I don't really know, besides numerical issues and the fact that I think the scheme is more like a one-way equation, they used plane wave decompositions for so they did rather than transform. There is a big difference between the two, very significant difference. So let me finish there. Further work on this, we have an abstract in SEG showing the case when we use multiple reflections once we started looking into that. We do need a 3D version, and I'm thinking of how to do guided optimization to automatically compute the background velocity, because that would actually remove humans from the cycle that really is very time-consuming, constructing the background velocity in the problem. So I'll stop here.
It's been a while since I knew this stuff, so it's trying to take questions. First is, can you do the Fourier transform migration using Larry variable velocities? I thought that required the uniform velocity. So you can take it out of the
Fourier transform I did was in time. So if you have X dependence, directly you cannot use it. Yeah. But the Fourier transform that I was talking about, this P hat, it was in time. So no.
The other one was, I guess that you were migrating gathers rather than migrating stack.
No. Of course. I mean, you have actual traces.
Right.
You don't want to do anything before that if you try to do it. Yeah. Yeah, essentially for numeric I mean, you never have raw data in reality, but I mean, in simulations, yeah, it's raw data, exactly what you record.
Okay.
So.
But I guess the question is that traditionally the stacking process was one of the ways in which we're trying to get a velocity.
Well, the stacking part here is hidden in this imaging condition. You integrate over all frequencies, and so that's where you collect the stacks, and this produces this image. So if you want to get the velocities, you need to you have multitude of data. So like in the first day of this conference, Martin was showing the lens, right? So there is no reflection from the lens. But you need to make things consistent. And the advantage here is that you have separate different frequencies. So the idea is to use low frequency model first, and then feed it into high and guide it through the frequencies.
You're stacking over the offset stack.
No, nothing of the standard stuff. Yeah. I mean, in seismic problem, you start with huge amount of data and you get a picture. So somewhere there is summation. Right. So this summation is hidden into the imaging principle. So.
You still show for your projection method essentially the constant coefficient case.
No.
If you have variable coefficients, the operator won't even be self-adjoint. And so the projections are not going to be normal.
No.
The example is variable coefficients, but the...
No, you misunderstood something.
Yeah.
This is a self-adjoint operator. It's a variable coefficient case. No, this is completely clean. You can always do that. So when you formulate wave propagation, you can always arrange things that things will be self-adjoint. So that's not an issue. And if it depends only on depth, then the old stuff works just fine. It's just that you cannot really do physics with just depth-dependent velocities and exploration things. Maybe for global seismology you can, but I don't think either. Now in the model, if you go back to the velocities, if you take a slice, horizontal slice, on the top it's uniform, or more or less uniform. But when you go for the salt dome, it's not. It's no longer the same function in x direction. That's the thing.
Okay, I suggest that we keep additional possible questions. Thank you.